this then. Okay, so first thing we're going to do on this is we're just going to focus on just the first derivative. Okay, so we do the first derivative like this. Okay, now this is one you got to review. A couple of things you want to remember on this. If you do a derivative of a log, what's the derivative of ln x? 1 over x. Okay, so if you do derivative of ln of something else, then it's a chain rule, so you have 1 over x squared minus 4x plus 5. Then you have to do the derivative of the inside part. You can just set that up there on that table. Okay, and you can do that in your head if you want to. So what you end up getting is 1 over x squared minus 4x plus 5, and then the derivative of the inside part here is going to be 2x minus 4. Okay, so there's really not any simplification you can do on this. So the first derivative, we'll just write that as 2x minus 4 all over x squared minus 4x plus 5. Okay, so we've learned how to do that. That's a chain rule for a natural logarithm. Okay, now what we're going to do is we're going to find critical numbers. So let me see if you guys know that. How do you find critical numbers? Set it equal to 0. Okay, so go ahead and write down your first derivative and set that equal to 0. Okay, now we have to solve this equation. All right, what do you do to solve an equation like this? Multiply by the denominator. Good. Okay. All right, so we do that. We get rid of the fraction. Okay, so we do that. Okay, that'll cancel that out. And the nice thing about this problem is we'll have a nice kind of simple critical number. So we solve the equation 2x minus 4 equals 0. The right-hand side is just 0, so we could add 4 to both sides to get 2x equals 4. So what's the answer to this equation in your head? 2. Okay, all right. So that would be our critical number. So that would be the place where the derivative is equal to 0. Okay. The thing that you have to pay attention to that didn't happen on this problem is you would also kind of have to figure out, does anything make that denominator 0? And what would happen is, and I'm kind of doing this in my head, not all students are going to see this automatically, but if I set that denominator equal to 0 and try to factor it, it won't factor. You would have to go the quadratic formula, and if you did, you would get imaginary numbers anyway. So this is something that I suggest that just kind of saves you time, because it takes time to solve that with a quadratic formula. It's not hard to do that. But let me show you what happens if I graph just the denominator, because these are always kind of good things to use your calculator for. So I'm going to graph that denominator. I'm trying to figure out if x squared minus 4x plus 5 is ever equal to 0. So let me show you what happens. Okay, that parabola never touches the x-axis. Now, like when you're in college algebra, when you learn to solve quadratic equations with a quadratic formula, if it has imaginary solutions, that basically means that the parabola will not touch the x-axis. And that means it's never 0. So like if you looked at your table of values on here, you're never going to get 0. You never are. Okay? But a lot of times, there can be times on a problem like this where there's something that'll make the denominator 0. And if you find something that makes the denominator 0, that's also a critical number. Okay? So you have to be aware of that. Okay? Okay, so it seems like we're okay with the critical number. Are we okay with getting x equals 2? Okay, derivative okay. All right. Now we're going to make a sign chart. So let's go ahead and make our sign chart. Okay, so we have x equals 2, and that would be where the first derivative is equal to 0. Okay, all right. Now what we're going to do on sign chart, we've done a bunch of this so far, is we're going to take test points on that. So give me a number that's less than 2. I don't care what it is. 1. Okay, let's go with 1. Okay. So plug into the first derivative, which is what I have highlighted in yellow. So 2 times 1 minus 4 over, and then that would be 1 to the second minus 4 times 1 plus 5. And you can do a lot of this in your head. You really can, but you can use your calculator also. The way I look at this is the numerator is negative. I can do that in my head. The denominator is positive, so we get a negative result, okay, from that test point, okay? Probably would have been a slightly easier to use 0. Anytime you can use 0 as a test point, that's a good idea. Okay, so what does that mean? If the first derivative is negative, what does that mean? It's either increasing or decreasing. Which one? Decreasing. There you go. Good. So we are decreasing here then, okay? So that's the purpose of the first derivative, is to analyze the graph where it's increasing and decreasing. Okay, all right. All right, now give me a test point bigger than 2. 3, there you go. Okay, whatever you want, okay? Plug it in again to the first derivative. The first derivative is what we got in the answer blank in yellow, so that would be 2 times 3 minus 4. And then that would be 3 to the second minus 4 times 3 plus 5. So I can see on this that I'm getting a positive numerator. That's 6 minus 4. The denominator is 9 minus 12, which is negative 3, plus 5 is positive 2. So we get a positive. So since the first derivative is positive, tell me what that means. You're increasing. Thank you. Okay. All right. Okay. So that again is the purpose of the first derivative, the critical number, and the sign chart. We now know the graph, kind of what it looks like. Okay. So now let's go down. Let's just kind of write the answers on this now. So increasing would be here. That would be 2 to infinity. And again, you're always naming the intervals with the x value, starting with the critical number. So that's 2 to infinity. Okay. And decreasing would be in this region. That would be everything below 2. So we would write that interval as negative infinity to 2, like that. Okay. So that's what the sign chart tells us. All right. Now, what you got to kind of do on this is you got to think about, well, is that 2 a minimum, or is it a maximum, or is it neither? Well, what's happening is the graph is decreasing, then increasing, and then you have that derivative equals 0. So is that a min or a max? It's a min. If you decrease, then increase, that's a local min. So we'll just write on that x equals 2. I'm not going to worry about getting the point. We're not going to care about that on that problem. Local max, there isn't one, because the only way you get a local max is if you increase, then decrease. Okay, and that never happens on the sign chart. Okay, so that's half of the problem right there. Are we okay with that? All right. Okay, so let's move on now to the second derivative, and the second derivative tells you about concavity. Okay, so what we have now is we have the first derivative. Remember, we got 2x minus 4 over x squared minus 4x plus 5 is the first derivative. So when we do the second derivative, we got to do the derivative again. Okay, what would be the correct rule to use to do the derivative of the first derivative? Quotient rule, exactly. So I'm going to write it down for reference. We have bottom times derivative of top minus top times derivative of bottom over bottom squared. So yeah, we got to go through all those details. So we need to get that done, and let's start working on the quotient rule. Okay, so when we put this in, we're going to have the bottom x squared minus 4x plus 5. Now you're going to multiply by the derivative of the top. The derivative of the top is just 2, so we got that. Then minus the top, and make sure the top's in parentheses. All these things need to be in parentheses. So we got the top, 2x minus 4. Now do in your head the derivative of the bottom, which is 2x minus 4. and then that will be all over the bottom squared. Okay, then we got to simplify this thing out and everything and kind of work on that a little bit then. Okay, so this won't be too hard to do. It's just got to be really careful with your algebra. So what I'm going to do is I'm going to distribute the 2. So that's going to give 2x squared minus 8x, and then plus 10, like that, okay? And then I'm going to write down my minus sign, and then in parentheses, I'm going to FOIL this. This is where you got to be really careful. So you want to go ahead and FOIL this. So we have 2x times 2x is 4x to the second. 2x minus negative 4 is negative 8x. Inside term is again negative 8x. And then the last term, negative 4 times 4 is plus 16. And then all over x squared minus 4x plus 5 to the second. Okay? Now, once I've put that in the quotient rule, then I need to distribute that negative and just collect all these like terms, and then we'll have a simplified derivative. Okay? So we're going to go ahead and do that. We're going to just bring down the 2x squared minus 8x plus 10. Be cautious about distributing the negative, so you're going to have minus 4x squared plus 8x plus 8x, and then that'll be minus 16. I almost screwed up on that. Okay, so I've got that. All over the bottom squared again. Okay, so now we'll put all our like terms together. So notice that in the numerator we have 2x squared minus 4x squared is negative 2x squared. Then if you put the x's together, it looks negative 8 and 8 cancels. You're left with 8x. Okay, then you've got 10 minus 16 is negative 6. And that's all over x squared minus 4x plus 5 to the second. Okay, so that is your second derivative. I'm going to write this up here in the answer blank and highlight that because we're going to need to look at that for the remainder of the problem. Okay, so you guys have done quotient rule before. You have to be really careful when you do this that you don't make any arithmetic mistakes. Okay, does everybody understand what I'm doing on quotient rule, okay? Okay, just be, the thing you got to be the most careful about is that 2x minus 4 times 2x minus 4, FOIL it, leave it in parentheses, then distribute the negative 3. If you don't do that, you're likely to make a mistake. Okay, so now what we do is we're ready to find the critical number. And so what you want to do is just take that second derivative. You want to write down the second derivative, and you want to set that equal to 0. Okay, so we got that. All right, now, what do we do to solve an equation like this? You multiply by the denominator, right? Okay, you don't want the denominator to be there, so it's very similar to what we did on the first derivative. You can kind of learn to do this in your head. Ultimately, what happens is you just end up setting the numerator equal to 0, but it's kind of helpful to certainly know why that is. Okay, so that'll get that to cross out. Okay, so now we're going to be left with focusing on solving the equation negative 2x squared plus 8x minus 6 equals 0. Okay, so what's going to happen in the algebra is you're going to solve a lot of equations and you're going to factor all the time on these problems. Is there any common factor that I can factor out of that? I got 2, 8, and 6. What do they all divide by? 2. You can take a 2 out. Now what I'm going to do is I'm going to take a common factor of negative 2 out. I'm not going to just draw 2 parentheses. Now you could go to the quadratic formula if you wanted to. But the best way to do this is to start by factoring out a negative 2 and make sure anytime you factor something, distribute the negative 2 in your head to make sure it's right. Then you're going to find that this thing that I'm highlighting right there, that's going to factor. You can draw 2 parentheses on that. So we'll have negative 2 times, okay, when I factor this, I'll have x and x to get x squared. I got 3 and 1 to get positive 3. And then I'm going to have 2 minus signs to get that. Okay, so now what I've got is I've got that. Now, can you tell me in your head, by looking at that, what the two critical numbers are? 3 and 1, right, okay. You don't have to do all this in your, write every single step on your paper. What you're doing is you're taking those two factors. You don't worry about the negative 2, that's a constant. So you do that, solve that equation, you get x equals 3, and then you get x equals 1, okay? So the second derivative, what happens a lot with the second derivative is it gets messy. Okay, that's not too bad, but second derivatives oftentimes get really messy. All right, so we got that. All right, is there any problem with that? You all done the quotient rule. I know you've done that successfully before. You just wanted, when you do a problem like this, you don't want to mess up because it just wastes time when you do. Okay. Okay, so now we're going to make our sign chart using the second derivative. So you want to go ahead and use these two critical numbers that we just got. We had x equals 1 and we have x equals 3. Okay, and that would be where the second derivative is 0 right there. Now I'm going to show you something a little different. Now you're going to still plug test points into the second derivative, but this is a valid way to do the problem. So I want you to get your calculator out and I want you to do this with me. This is important. If you want to save yourself a little work, then what you can learn to do on a sign chart is you can actually graph the second derivative, and we can get the sign chart with that. Well, we don't have to do anything. We can just trace out test points. So go ahead and go to Y1 on your calculator, and we're going to graph the second derivative. That's what I have highlighted in blue. So you want to go ahead and put in negative 2 x to the second, and then plus 8x minus 6, and then divide by, and then the denominator you would want to put in just the way it is, parentheses x squared minus 4x plus 5 to the second power. Okay, and we're going to graph that in a standard window. Okay, so what we're doing is we're going to graph the second derivative so that way you can do this sign chart very fast. That way you don't have to plug in the test points and do all the arithmetic. Okay, that's just an alternative way of doing that then. Okay, so I'm going to go ahead and just do zoom 6. That's going to give me the graph of the second derivative. Now, what I'm going to do is just, this is kind of a way to save a little bit of time on here. So what I'm going to do is give me a test point that's less than 1, your choice. 0, very good. Now look at this. I can trace at 0 and I get a negative answer. Isn't that easy? Okay, it saves you tons of time because you're going to get sick of doing sign charts by hand because all it is arithmetic anyway. All right, give me a test point between 1 and 3. 2, okay, you guys aren't creative. You always just give me simple whole numbers. That's fine. Trace at 2, you will get a positive number like that. All right, now let's take maybe 4, trace at 4, you're going to get a negative number. Okay, that's an easy way to do a sign chart. On a sign chart on a test, really what I want to see is the critical numbers and minus whether it's negative or positive. You can do that with arithmetic by plugging test points into the derivative and doing the arithmetic, or you can learn to do it this way. This way is more accurate. You're not going to make any mistake this way. Okay, so that's what I recommend. Okay, so what we do now is what we learned last time is I taught you these two faces. Okay, so if the second derivative is positive, you are concave up. That means the graph is happy. Okay, if the second derivative is negative, the graph is sad at that point in time, so it's concave down. So those two faces right there tell you how to do the problem. So what you're going to have is your concavity goes like this. You're going to be down, then you're going to be concave up, then you're going to be concave down. Okay, that's all you got to do on that. So now we can pretty easily write our intervals. Okay, tell me where I'm concave up based on my sign chart. Where to where? 1 to 3, good, okay. One of the reasons that you see me always draw a box around my test points is so that I don't confuse my intervals. Like it's the 1 and 3 are the critical numbers, so that's where that is, okay? All right, what do you think about concave down? Okay. There you go, outstanding, okay, all right. So we got the negative infinity to 1, and then we got 3 to infinity like that. Okay, that's how we know the answer to the problem. Okay, do you guys remember what an inflection point is from last class? Okay, why is it an inflection point? Because the concavity changed, good, okay. So what happens is the concavity changed from down to up and then up to down. So you have 2 inflection points. So, and when I say give an inflection point, you have to give me both the x and the y value. So we got that. Now what we're going to do, and what I recommend you do, to get the y values, you have 2 choices. You could go f of 1 and plug into the original function, which is ln of x squared minus 4x plus 5. You could do that if you wanted to. You could do f of 3, again, by plugging that into the original function. So that would be ln of 3 to the second minus 4 times 3 plus 5. You can do that if you want to. This is what I think you ought to do, though. Okay, so let's do something else on our calculator. This time, what I want you to do is graph the original function. And that way, we're going to check our answer to the whole problem anyway. When you're doing your homework, you want to tell you're right on this. When you're doing this on a test, you want to know that you're right. So go ahead and graph the original function, which is ln of x to the second minus 4x and then plus 5. Okay, like that. All right, and just do a standard window, zoom 6, like that. Okay. Now, if you look at this graph right here, first of all, let me just kind of show you what's happening on this. Let's look at increasing, decreasing. Decrease negative infinity to 2. Does it look like we're decreasing negative infinity to 2? Yeah. Increase. Does it look like we're increasing 2 to infinity? Okay. Concave up. Is there a part of the graph that has a smile? Yeah, right there. Isn't that kind of smiling? Concave down is this. Okay, if you kind of have half of the frown, you're going down, up, down like that. Now, the points of inflection are kind of difficult to see on this, but here's the easy way to do it. On our sign chart, 1 and 3 is where the points of inflections are, so just trace it 1, and when you trace it 1, that will give you this, and it's okay to get a decimal. You're going to have 0.69. We're just going to round that. Then we're going to trace at 3, the other inflection point, and that'll also give 0.69, and then the problem's done. Okay? So the calculus is sort of training you to see how derivatives tell you what graphs look like. Okay, that's the idea. And then we'll do one kind of good business example towards the end of the class today on concavity. That's a pretty important thing to learn for a business major. Okay? Okay, any questions? Okay. Either get a picture or get that written down. Everybody got that okay? What's that? We didn't do this problem last time. Okay, we skipped it is what we did, okay? Because I wanted you all to start working on a problem, okay? All right, everybody got it okay? All right. That one right there is probably a little harder than the other examples I did. Okay, well, let's just kind of work on this one together, and we'll do that. And I think we already kind of started the problem. This one is one that I wanted to give you that's probably a little bit easier just to kind of work on. Okay, so let's go ahead and just kind of do this one, I think, together on here. Okay, so what's the first derivative? You can do that in your head. There you go. Good. Okay, so that's your first derivative. Let's go ahead and do the second derivative. What's the second derivative? 12x squared minus 8. Okay, so you don't have to work very hard on the derivatives on that. Okay. Okay, now what do you do to find critical numbers? I'm going to keep asking the question. You set the derivatives equal to 0. Good. Okay, because I think last class we weren't quite there on that or something. Okay, so good. You're always looking for where the derivative is 0 or where it's undefined. Now, what you're going to find, don't forget about the undefined. These are defined everywhere. X can be anything, so we just solved these two equations. So what happens to some students is algebra background issues affect their ability to factor. So how do you factor 4x cubed minus 8x? Yeah, you can take a 4x out, okay? You have 4 as a common factor, and there's an x in both positions, so you take that out. Okay, now in your head, what do you multiply 4x by to get 4x to the third? That's got to be x squared. What do you multiply 4x by to get 8x? That's going to be a 2, okay? So that's something that you can't slip up on. You're going to factor like crazy when you're doing this stuff all the time. So now what you do is you have two factors, like we've been doing a lot, and you set each factor equal to 0. So we're going to solve the equation 4x equals 0 and x squared minus 2 equals 0, okay? So this one you could divide by 4. You would get your first critical number would be x equals 0, okay, like that, okay? Second one, and I think we worked on this a little bit in class, and I think this is what some of you weren't doing well on. It was this. You just isolate, and then what do you do to both sides? How many answers do you get? 2. Okay, that's another question that a lot of times students just forget about. You have the plus minus. So you also have these critical points. You have negative root 2 is another critical point, or critical number, and x equals square root of 2 is another one like that, okay? Okay, so we're going to go ahead and do that. We're going to go ahead and just kind of work on both parts of the problem at the same time on this, okay? So we've got our critical numbers. So let's go ahead and let's do this now. Let's go to the second derivative. Again, we're going to add 8 to both sides. And we have 12x squared is equal to 8. Then I can divide by 12. Okay, I can reduce the fraction. 8 over 12 reduces to 2/3. You do want to do that. That's the same idea. Take square root of both sides. You do get 2 answers, so you're going to get x equals negative. You have that plus minus there. So you have negative root 2 over 3. And then you also have x equals positive root 2 over 3 like that. Okay, so compared to the problem I did with the logarithm a few minutes ago, this is a little bit more straightforward for students typically, okay? Okay, any questions about what I did with derivatives or finding critical numbers? Okay. Now, I'm going to have you all finish the problem. So let me just kind of get you set up on this now. So you're going to do your sign chart for the first derivative. So that means your critical values, we got 3 critical values on this. We got x equals 0. Make sure you always put this in order. You had x equals negative root 2. And then you had x is equal to, and that should be negative root 2 right there. So that's negative root 2. Okay, so we got negative root 2, and then over here we got positive root 2 like that. Okay, now what you all are going to do is you're going to do test points. Now, you know, root 2 is like negative square root of 2 is like negative 1.4. Positive square root of 2 is like 1.4. So you all need to do test points plugged into the derivative, okay? I'm just going to start you off on one of them, okay, just so that you kind of know what I'm doing on this. And you can use your calculator to do this. Or if you want to graph your first derivative, and just trace out your test points and do your sign chart that way, you can. It's up to you. So I'm just going to show you one way to do this. Let's use like -2 as a test point. That's less than the square root of negative square root of 2. So you just plug into the derivative. You would do 4 times -2 to the third minus 8 times -2. That would be -4 times -8 plus 16. That would be a positive right there. And then that would tell you whether it's increasing or decreasing. Okay, so I'm going to have you kind of spend a little time finishing up the problem. When you do concavity on the second derivative, you want to work with -√2/3 and x equals +√2/3 like that. All right, so let's go for it and see if we can finish that up. Now, if you want to get the problem done a little bit faster, then the best thing to do is when you do your sign charts, you could graph the first derivative and then just trace out your test points to get your pluses and minuses there. On your second derivative, to do that sign chart, all you got to do is graph the second derivative and trace test points. And you'll do it fast. That's what I'd recommend. Okay? All right, let's work on it. Let's see if you know what's going on or not. Okay? What's that? Did you graph the first derivative? Okay. It may be. I got a number, but it was negative. That's okay. That's all you care about.
But you got positive.
Oh, whoops! I messed it up. Okay. So, your window's kind of funny. So let's just go to Zoom 6. You were tracing a point that was out of the range. So yeah, if you trace -2, it's negative. Yeah, that's negative. I did the arithmetic wrong. Okay. So yeah, you should be okay now. Okay. So again, that's the easy way to do it, is just graph this in a standard window and then just trace out your test points. Okay. And then you'll get your table of values perfectly 100% correct, as long as you graph it correct on your calculator. And I'm going to put up the answers and we'll kind of look at the key things. So we kind of together, we went through everything on finding the critical numbers. Okay, so you just want to kind of see what you have here. And everybody, I think, got the sign chart okay. I didn't see any issues with that. So once you get your sign chart, the first derivative sign chart tells you about the graphs increase, decrease, max, and min. So you should have had minus, plus, minus, plus. Either you plugged in test points like you see I did here, or you could graph that first derivative. So one thing that I want to kind of mention on here, again, because I want to give you some strategies that'll help you speed up the process of figuring these sign charts out. So if you graphed the first derivative we got 4x to the third, and then minus 8x. So if you just graph that in a standard window, then the thing I want you all to know is I know if that's the graph of the first derivative, I know that it's minus, plus, minus, plus without even tracing. Here's why. If I take a test point, -2, that just means I have a negative y value, right? All it's going to spit out when you trace -2 is that y value, which is negative. Okay? If we use the test point of like -1, I use that right there, I can tell that y value is positive. So this is going to be negative, positive, negative, positive. Because all the sign chart's doing is the test points are finding y values, and they're either negative or positive. So if you graph the first derivative, you don't even have to trace in those test points. You just say negative, positive, negative, positive. Does that make sense? Okay, save even more time by doing that, okay? All right, so now what we get on this then, as you can tell, increasing is going to be where you're positive. So that increases from negative square root of 2 to 0 and 2 to infinity. So you should have got that answer. Decreasing is where the first derivative is negative. That will be negative infinity, negative √2, and then 0 to √2 like that. Okay, and then for mins and maxes, you got to go through and do this. So what you can kind of do is just kind of think about what your graph looks like. The graph is decreasing, hits a low point, increases, decreases, like that. So you have two minimums. The minimums are at negative root 2 and 2, and the maximum is at 0. Now, what you can do to get those y values on that is, if you want to get the y values of the local min and max, then you go back and graph the original function. So the original function was x to the fourth, and then minus 4x to the second, and minus 2. So I'm now going to go back and just graph the original function in a standard window. And see, now I can trace out those values, okay? You can use your technology to help you with a lot of things on these problems. So if I trace at negative square root of 2, okay, what's going to pop out is negative 6. So that's how I got that, okay? A lot of times students get confused about when do I plug into the derivative? When do I plug into the original? The only time you plug into the original is if you want to find y values on the original graph. So that's why I'm working with the original function now. And also, when you do this, you're checking the problem set. You can tell that this graph is, like the sign chart said, it's decreasing, then it's increasing, then it's decreasing, then it's increasing, right? Okay? The purpose of the derivative is just to help you to figure out whether it's increasing or decreasing. Yes?
So for the local mins to find the y value,
you just plug into the original function, or you can graph.
Can we trace the derivative?
No, not the derivative. Okay, if you want to get these y values here, you're going back to the original function. The only time you plug into the derivative is if you're building the sign chart. Okay, so these things, the negative 6 and the negative 2, that all comes from the original graph. Okay, that's the fast way to do it. The other way to do it is just plug into the original function and calculate. Okay, those are your two choices. Okay, but hey, this is the year 2023. Okay, you can do this. You don't have to do as much arithmetic as you used to have to do. Okay. Okay, so what would have happened on the next one here is you had plus minus plus, so that means that you're concave up in these two locations, and then you're also concave down in there. Okay, so the answer I got for concave up was negative infinity to negative root 2 over 3, and then root 2 over 3 to infinity. Okay, and then concave down was negative root 2 over 3 to root 2 over 3, like that. Okay, and again, just to show you this, if I was to graph the second derivative is 12x to the second minus 8. If I graph the second derivative, that already tells me, I pointed this out when I was kind of walking around. I mean, I want you all to know it, that this is the graph of the second derivative. So the y values are positive, y values are negative, y values are positive. Okay, you can go by looking on that if you want to. So then when we go back to the original function, like I had a minute ago, let me just put that in one more time. So we have x to the fourth, and then minus 4x to the second, and minus 2. So back to the original graph, then I can trace out those inflection points to get those y values, and that's what I ended up doing on that. So, so what I have is, like if I traced at negative square root of 2/3, that'll give the y value negative 4.2. And I'm okay with the negative 4.2, okay? If I want to get a y value on a min or max or on an inflection point, you're going back to the original function. Okay, that's a point of inflection. You can tell by looking, the graph changes from concave up to concave down. Okay, and then you can do the same thing with the other one. You could trace at positive square root of 2 over 3, and you get the same value. Okay, so that's how we got it. Now, you notice on my answer, I had negative 38 over 9, which you don't have to have, but let me show you what I did. You end up getting negative 4.222. You just put a whole bunch of 2's in, and if for whatever reason you needed to get an exact answer, then you just type that in, you go math, and then you convert that back to a fraction. That's how I got it. Okay, so that's another thing to just kind of mention on that problem. Okay. Okay, so that'll kind of wrap that up. Let's go ahead and do our 10-minute break now. And we'll get back. Please come back at 9:30, and then we'll get this finished up. Okay. We've done kind of the parts of the problem that take the most work. The other things we're going to do will be a little bit less time intensive. Are you, say that again? Yeah, okay. Yeah, negative 4.2. They both had the same Y value. You can see that kind of on the graph. So did you all know that CCD is going to quit requiring business majors to take this class? No. But let me tell you something. Let me tell you something.
I feel like I started a bunch too early.
Let me tell you something, okay? If you're going to transfer to a 4-year school, then you'll have to take it there. And you all are wise to take it here now. Trust me. I'll tell you exactly what's going to happen. This makes me mad too, because this is just politics, okay? They're afraid that we're not giving out enough associate's degrees because people struggle with this class because it's hard. Calculus is kind of hard. What's going to happen is they're going to let you either take college algebra or even finite math, and business majors are going to start taking finite math. And then they're going to get their degree easier. Then they're going to go over to Metro or CU Denver or wherever, and then they're going to be in bad shape. I'm not kidding. Okay, they're not taking away the business calculus requirement at 4-year schools and universities. Okay, and the class is harder over there. If you go to CU Denver and take this same class, you do like a 3-hour final on a Saturday morning. Yeah. So you're wise to get it done. But I'm afraid what's going to happen to me starting in the fall is either I won't have any classes anymore because they'll get canceled because nobody will take them anymore, or maybe I'll just have one class with 5 people in it. I don't know. Well, I can teach anything else, but I just teach this pretty consistently. I teach Calc 1 and Calc 2, and I can teach anything else, But, I've just been teaching this because a lot of teachers don't want to teach this class. That's interesting. Yes, because it's a class where a lot of people, what they do is they wait till the end of their associates to take it. They take a big gap between college algebra. They take college algebra and they say, I've had enough math for a while. Then they get in here and they've forgotten all their college algebra. Sound familiar? I mean, you always advise people, whether they like it or not, to take math in a row. Don't take a gap, no gap. So anyway, so I think I may have lost a few students in this class drop because of that. Or people are already dropping. Oh, thank goodness. Okay, but I know what's going to happen. You guys are wise to get it done now. I've taught this class over at Metro and CU Denver before, on a part-time basis. I used to teach over there some. And it's, same curriculum, but it's a little harder.
What's the EV survey of calculus and isn't that different than just calculus?
Yes. It's designed for business students. The main difference is there's no trigonometry in this class. My Calculus 1 class is for more engineering and science majors. So there's trigonometry and it's harder. Calc 1, I mean, you'll learn. If you took Calc 1, you'd learn all the derivative stuff we've learned. You know, it's just, you know, all the things we've learned are a little harder, you know, in Calc 1. So, you know, so anyway, you guys are wise to get it done now because it's transferable. And if you move over after your associates, if that's what you're going to do, then you don't have to worry about math at a university. That's a good thing. Trust me.
I was looking at a degree at MSU, and it's a transfer degree, and I think they require finance for it. So you can
They'll take college algebra though.
oh,
Yeah. Generally, we used to have all the business students take finite then calculus, but finite doesn't prepare you for this class as good as college algebra does. That's why we do that. And what they do at CU Denver is they have a college algebra class for business majors, which is more intense than finite, but it's designed to prepare business students a little better for Cal. Finite doesn't prepare you very well, in my opinion, for whatever that's worth. So anyway, don't give up.
Get until tomorrow evening to complete the River 2.7. Anyway, we could just keep
Possibly.
Keep it
Have
open
I?
just for one more evening.
Yeah, you need to send me an email sometime today. Okay, and I'll take a look at that. Okay, all right.
when does that take effect that they're not requiring them?
What's that?
When does that take effect?
Just recently in this semester. I don't know who decided it either, but it's kind of interesting. I don't know if it's a CCD thing or a system thing. It's probably a system thing. You just have to do it over at your 4-year. If you don't do it here, you're just going to have to do it over there.
Swap classes between the 4 and 2.
Yeah, they'll like this is transferable. This class, if you go to Metro or CU Denver, any place in Colorado, and most universities anywhere are going to accept this class. Those transfer agreements, we make agreements between colleges. So like college algebra is transferable. This class is transferable. So if you go to CU Denver and they say you're supposed to have business calc, you took it at CCD, then you're good. Okay, so that's what you want. You want to get this done. Because what happens, like I said, all the time, people, even they get in their 4-year degree and they wait till they're a senior to take any math. And they've taken everything else, and then it's been so long they've been in math, they struggle with passing it because of that. Yeah, that's just kind of what happens. So, too bad. Yep, yep. Yep, and you have to confront it. You can't run away from it. You have to confront it. Math is not easy. That's the thing about it. I mean, some pretty smart people invented calculus. Yeah, so it's learnable. It's learnable, but it takes hard work. Okay, so let's go ahead and go to the next page here, and then we'll start back. Okay, so on this next page, what I want to show you here is, we're not going to do a lot of calculation on this. We're just going to observe graphs and kind of work with this a little bit. Okay, so basically, if you have an inflection point, so what I want to show you on this right here is there's a couple of things are happening on this one graph right here. Okay, first of all, you might make a note to yourself that you are concave up there, and then you are concave down right here, okay? So remember, an inflection point is a point on the graph when the concavity changes. So this is an inflection point right here. Now what happens if you draw a tangent line at an inflection point, it'll slice right through the graph, and what'll happen is part of it will be below the graph and part of it will be above. So you're going to kind of see that this piece right here is above the graph. This piece right here is below. That's what inflection points do. Here's another example. Okay, right here you would be concave up. Right here you would be concave down. Well, what happens is if you draw a tangent line, it slices through the graph, and then again you're going to see that part of that tangent line's above and then part of it's below. Okay, the reason I go over that is because a lot of times students have a hard time when they're looking at a graph figuring out where an inflection point is. Okay, so any other place, like for instance, if you have a tangent line there, well, you're always below, aren't you? Or if you have a tangent line here, you're always above. Or if you have a tangent line here, you're always below. That's what's special about an inflection point. It slices through the graph in that way. Does that make any sense to you? Okay, now that's an important thing to visualize then. So what we're going to do is I'm going to go through an example, then I'm going to let you do an example. You just have a given graph. Now I think this very problem right here is on the web work assignment that I'll post today for this. Okay, I think this is the same thing. It was kind of hard to find a graph that was easy to figure out inflection points on. So let's start with increase-decrease stuff. Okay, students generally are pretty good with that. So I'm going to highlight in yellow where we're increasing. So you can tell, you know, from right to left, it's just like you're going uphill. You're going up a roller coaster right there. Okay, so if you name the intervals, you're always naming intervals with x values. So increasing, we would say one of those would be 1 to 3. Okay, right there. All right. Then we would also have to say, now what happens here, this is kind of important. This is something you got to be careful about. What's happening is you have these three places on this graph where the derivative is 0. So you would be increasing from 4 to infinity, but you have to break it into two intervals. You would have to say 4 to 5. Then you would have to say 5 to infinity like that. Now I'm going to assume that graph is going on forever like that. So you might want to put those arrows at the end of the graphs like that. All right, so that's why you would do that. And the reason you have to do two intervals is because the derivative is 0 right here, but the derivative is positive everywhere else. So if the derivative is 0, that doesn't mean you're increasing or decreasing. It's neutral. That's why you have to break that up into two intervals, okay? All right, now decreasing is pretty easy for students to see generally. I'll just kind of highlight this in blue. So we'd have that, then we'd have that like that. All right, so what would be the intervals? What's this first interval going to be? Negative infinity to 1, good. And what's the second interval going to be? 3 to 4, okay, all right. So we got that, all right. Now we're going to look at kind of local mins and maxes. So what a local min is, a local min has to be a point on the graph where you decrease and then you increase. Is there any points on the graph where the graph changed from decrease to increase? How many points did that happen at? 2, okay. Right here is a local min, and right there is a local min. Okay, now I'm saying use points, so get the point then. So that would be the point 1, 2, let's see, that looks like that's a 4. So that would be the point 1, 4 would be a local minimum. And then this point right here looks like that would be 4, 3. Okay, so that's what a local min is, okay? Low point on the graph where the graph changed from negative to positive, decreased to increase. Okay, a local max is this situation. The graph increases, hits a high point, then decreases. Does that ever happen? Yeah, how many times does it happen? Only once, okay, right there. So that point looks like that is the point 3 and then 6. Okay, so you only have one local minimum right there. Okay, so that's the idea. All right, now I'm going to go ahead and skip down to H and I just to kind of talk about what an absolute, we've already talked about what absolute or global is. So if we're looking at a global minimum, what does a global minimum mean to you? The lowest point that it ever hits, right? Okay, what's the lowest point that this graph ever hits? 4.3, right. Okay, so this thing right here is also a global or absolute minimum. And you can be both. You can be a local min and a global min at the same time. So that would be at the point 4.3. Okay, global max. That means the graph hits a high point. Does this graph ever hit an absolute highest point? No. No. I had you add these arrows on here on purpose. What does that mean? It means the graph goes up forever, okay? So you have to pay attention to this. There's no endpoints on this. This graph just keeps going up forever, so there's not one. Okay, you got to pay attention to that, okay? The graph doesn't go down forever. That you have an absolute low point, but you don't have an absolute high point. Okay, does everybody understand that? Okay, you got to pay attention to that, all right? So now I'm going to erase all this stuff, and what I'll do is let's look at the concavity, okay? So the thing that happens a lot of times with students on this is they have a hard time locating points of inflection, okay? So concave up is going to be the smile, and that would be there. That would be one place where you're concave up, okay? Another place you're concave up is right here, okay? Because, and one thing that's kind of worth either making a note to yourself of or just kind of making sure that you're aware of this, if you're concave up, there's 3 ways the graph can look. It can be like the full smile, or it could be half of a smile. Okay, it can be any of those three shapes. Those are all concave up. Concave down is going to be like the full frowny face or half of the frown. Okay, sometimes students don't make that connection. Okay, so those 2 things right there, I got the full happy smile and I got half of a smile. Okay, then concave down is going to be where you either have the full frown, right there's a full frown, and then right here is a half a frown, right there. So your points of inflection are going to be the places, they're points on the graph where the concavity changed. One of the hardest things for students to do is to figure out where the points of inflection are. And this is what I recommend you do. Draw a tangent line at those inflection points. Now notice that that tangent line, part of it is above the graph, part of it's below. That's what will happen on that. That's why it's an inflection point. The same thing happens here. If you draw a tangent line there, see you're below the graph there, and then if you continue it that way, you're above. So that's why it's important to know how a tangent line looks at a point of inflection. Okay, now we're ready to write our intervals then. So when we do concave up, again, we write these, and I think on this problem again, we had the arrows going on forever. So what would be an interval for concave up? -2. What else? There you go. 5 to infinity. Okay, like that. Okay, and then concave down would be, and you have to break this up into 2 intervals. You would have this region here, which would be 2 to 4. Okay, now there's no derivative there. There's a sharp point there. So if you have no derivative, then you're not concave up or concave down there. So the other place would then be 4 to 5, like that. Okay, so that's your concavity. That's how that changes on the graph. All right, your points of inflection, we identified. Those are the things I have right here. So the points of inflection look to be the point 2, what is that, 2, 5, 1, 2, 3, 4, 5. So you got the point 2, 5. And then this point right here appears to be 1, 2, 3, 4, 5, so the 0.55. So those are your two inflection points on your graph. Okay, so generally what I find on this sometimes is students usually increase, decrease is usually fine. Concavity, there's a little struggle understanding where inflection points are, so you have to understand how that tangent line goes. All right, do we have any questions? Yay, nay? Okay, all right, let's go to the next page and I'll let you try to do a problem. And there's one thing I want you to do on this before you start this. This time, what I want you to do is have endpoints. Okay, so this graph is going to have endpoints. It's not going to go on forever. I want you to just do the problem that way then, okay? So just kind of see what you can get on that and compare answers, and we'll see if we're on the right track with that. You're going to do the same thing. Increase, decrease, min, max, global min, max, and look at the concavity. Okay, well, let me kind of see how you're doing here. Okay, doing good so far. Everything's right so far. Everything's right so far. Good job. Okay, keep going. You're right so far. That's right so far. Just be sure you close those. And that's always parentheses. Anytime you do increase, decrease, or concavity, it's always going to be open intervals. Okay, now one thing on that you didn't catch is these are going to be endpoints. So, okay, so that's going to go from 4 to 6. Okay. Yeah, you want to put endpoints. Just put those endpoints on the end. That's one thing you didn't catch. Okay. But you're right. I mean, your second one is right, and your third one is right, and D's are right. So everything's right. So far. Yes. You always use parentheses. You don't use bracket ever when you're naming an interval of increase, decrease. Now the reason on that is because it's hard to tell what the derivative is. The derivative may be 0. You can't tell. Okay. So just always use, just kind of exclude the endpoints. Just always parentheses. Okay, let's see what else we got here. Okay, now I is not right. So you need to figure out what's wrong. Everything else looks right.
So this is the point.
Yes, exactly. You did a good job there, kind of putting your tangent line on there. Okay.
2, 3.
Well, concave.
Just for the point of inflection.
Yeah, that would be a point of inflection. That's what concave is. that, right there, I'm not sure. Yeah, the local min is right here because the graph decreases and increases. So that point, oh, local max, I'm sorry, the local max is there. And that's not a right y value, that's just 1, 2, 3, 4. And that's just 1, 2, 3, 4. Okay. Everything else I think we got okay.
Yeah. Yeah.
Now you only have one place where the concavity changes. What yours is concave up, right there, and concave down, and concave down. Yeah. The only place that it changed is right there. That's an inflection point right there. Because if you draw the tangent line, it slices through the graph away. So you're going to be concave up from 0 to 2, concave down from 2 to 4, and then 4 to 6.
Okay, so for the point of inflection, we're going off of the concavity.
It's where it changes, exactly. If the concavity changed, then it's a point of inflection. See right there, it's down and then still down. So that's not a point of inflection. The only place the concavity changed is there. It changed from up to down.
Okay, I thought point of inflection was anywhere it changes, so like from here it goes decreases, increases.
But
So
you're,
we're going
no, that's
one point.
concavity. We're talking about concavity, not increased either.
Okay.
Okay, let's see, I is not right. I is a global maximum. So a global maximum, you're pointing at it, so what is that point?
Yeah.
It isn't 3, 4. That's a local max. A local max is 3, 4. That's your global max right there. That's the point, what, 6, 6?
Yeah.
Okay.
Why wasn't I driving off this one?
Yeah, so the thing on this is global just means the highest. That's the highest point. That's a global min right there. And you all have the global min, right? That's 4, 1. But a local min means the graph decreases, then increases. So that's a local min. That's also a local min because the graph goes from decrease to increase. This is a local max because the graph changes from increase to decrease. Okay, so you got your local mins are right, you got your local max right on there. But absolute, now you can have a point like this is both a global minimum and a local minimum at the same time. All global means is it's just a point on the graph that's the highest or the lowest. That's all that means. Okay. Okay. Now you got to think about your concavity a little bit. Just kind of look at the graph, how it's smiling and how it's frowning. Just think about that for a minute. See what you get. Okay, did you figure out that last one? There you go. That's right.
So a global main max doesn't have to increase or decrease or decrease.
Exactly. A global can be an input. A local cannot be an input. Because on a local, there has to be something going on the left and right of the point. That's why it can't be an
But a
input.
global is just
Yes, highest point or the lowest point. That's what it says. Okay, inflection point is where the concavity changed. So the only place the concavity changed was here. Because see, your concave up on 0 to 2, you got that interval right, and then your concave down from 2 to 4. That would be where the concavity changed. And remember what I said is if you draw a tangent line at an inflection point, part of the tangent line will be above the graph, part of it will be below. That is your only inflection point on that problem. This is not an inflection point because the graph didn't change its concavity. You're down, and then you're still down. So that 0.41 is not an inflection point. It's got one inflection point. That's it. Okay? Think you got everything done? Okay, all local means is find a place where the graph increases, it's a high point, then decreases. That only happens one place. That's it. You wrote that on. That's it. Okay. Whatever that point is. 3, 4, I think. Okay. Okay, so pretty good job. Let me put the answers up here. Okay, so I've got the answers up here. Go ahead and just kind of check over your paper, make sure you got everything right. I kind of went around and checked, and everybody got increase, decrease right. A little bit of confusion on local mins and maxes. I tried to kind of clarify that for you. So you have two local mins. Sometimes students will see that sharp point and they say, that can't be a min. Yeah, it can. Okay. All that a local min is the graph decreases, increases. So what if it's a sharp point? It doesn't make any difference. So these are your two local mins. And then the local max is here because the graph increases, then decreases. When you have a local, oh, that's 3, 4. I'm sorry. Yeah, 3, 4. Okay. So we got that. All right. So are we okay on what we mean by local min and max? Okay. Now notice the global minimum is just the lowest point there ever was. This is global min right here. It's also local at the same time. So that's the global min. And then the global max is the highest point the graph ever hit. So it's there. Okay. That's it. All right. Now, concavity, the thing on concavity, it kind of goes like this. So let me go through a couple of things on concavity. So again, you just got to kind of visualize where's the happy face. A lot of times students want to think that the concavity stops at 1. It doesn't stop at 1. It continues to be happy. Okay? All right, the graph's happy. It starts becoming sad at 2. Okay? So the idea is what I said is if you draw a tangent line at an inflection point, what did I say about that tangent line? Part of it's above the graph, part of it's below. That's what makes that a point of inflection. Then what happens is now you're sad. You don't stop being sad at 3, you continue to be sad. You got the whole frown. And then from 4 to 6, well, you're halfway sad. Okay, if you want to think of it that way. Okay, so your concavity, you should have got the interval concave up was 0 to 2, and then concave down, you should have 2 intervals, 2 to 4, and then 4 to 6. And the reason you have 2 intervals is because there's no derivative because of that sharp point like that. And you only have 1 point of inflection, that's 2, 3. That's it, okay? All right, are we okay? Okay, you just got to get all those definitions in your mind. That's the key. Okay, next thing we're going to do is this is an exercise to further help students understand the language of calculus and how it relates to graph. That's what the purpose of this activity is. And I've given you problems like this before. What I always recommend you do is if I give you a couple of statements before you draw a graph, you just write down what it means. So this statement 1 says the first derivative is greater than 0. If the first derivative is greater than 0, what does that mean to you? Increases. Good. So let's write that down. So we know that this graph is always increasing. On negative infinity to infinity, this graph is always increasing. Okay? Statement 2 says the second derivative is greater than 0. What does it mean if the second derivative is greater than 0? Concave up. Okay? Second derivative tells you about your concavity. So this just means you're concave up. So what you have to do is you have to draw a graph that's always increasing and always concave up. Now, this is something I recommend you write on your notes. This is why students a lot of times have a hard time putting this together. So if you're concave up, your graph can look 3 ways. This is kind of an important thing to write on here. Now, in this case, you would be decreasing. In this case, you would be increasing. And then in this case, you would decrease, then increase. Okay? So in this particular problem, you got to figure out which shape it is. Okay? You're increasing and concave up. So out of those 3 shapes, what would it have to be? The third one, exactly. So what you do on your graph is you just draw that shape. And it doesn't matter how you draw that shape, where it crosses the x-axis, where it crosses the y-axis, it doesn't even have to. You just draw that shape, okay? So that's something that's real important. One other thing that's kind of helpful to write on your notes is the same thing for concave down. You could have a situation where you are increasing, then decreasing on your concave down, or you could have concave down and increasing, or you could have concave down and decreasing. So those are good things to write down. When you do these problems, it's not a bad idea to write those three possible shapes down, and it helps you put this together, okay? So again, what we're trying to do is put this together, just seeing that we can translate the language about what derivatives mean into a graph. You're learning a lot about function graphs when you learn about calculus. Yeah, okay. Any questions on that? Get a picture of that too if you want to. Okay, let's do the next problem. Okay, so again, and when you do this like on a test, like on a future, say, test 3, because I definitely give a problem like this, I always say that, earn partial credit. One way to do that is tell me what each statement means. What does this first statement tell you? First derivative is less than 0. What? Decreasing, thank you. Okay, second statement, second derivative is less than 0. What does that tell you? Down, concave down. Okay, second derivative is concavity. Okay, third statement, first derivative is less than 0. What does that tell you? Decreasing still, right? Still negative. And how about statement 4? Second derivative is greater than 0. Concave up. Okay, that's what you have to know. Okay, now the challenge of the problem a lot of times is students sometimes struggle to figure out what the graph's going to look like because they try to do it all in their head. So here, this is one thing that I would recommend. First of all, this graph looks like it just always decreases. Okay, so you got to think about, okay, we got a graph that's always decreasing. Okay, but the concavity does change here. So what you have here is you're changing from concave down to up. So you're going to be concave down from negative infinity to 0. Then you're going to change to concave up from 0 to infinity. So what you have to kind of think about is, well, what's it going to look like if we are concave down and decreasing? What do you think it's going to look like if the graph's always decreasing and we're concave down? What is that going to look like? This, right? It's going to go like that. How about if you're concave up and decreasing? So you can look at what I put on the previous thing here. So if you kind of look at this, this is a good way to look at this. Your concave down and decreasing would have to be that shape. Okay, then you are concave up and decreasing. Concave up and decreasing would have to be that shape. So what you have to do is you would draw your graph like this. You would have to draw the concave down and decreasing. Okay, then you'd have to have an inflection point. Then you would have to be concave up and decreasing. So it'd have to look like that. And again, you have to kind of do that inflection point so that that slices through the graph like that. Okay, so it's got to slice through like that. So that's what that graph's going to look like. It's going to have that shape to it. Concave down and decreasing, concave up and decreasing. So it'll be very helpful if you refer to these 3 shapes that I had you draw on that. Okay? Any question on that? Okay, I'm going to let you try the problem on the next one. Now let's see how we do. Sometimes this is not easy for students, but step 1 is to write down what everything means. Okay? I think at this time I'm giving you 6 statements. It's a good idea to write down what every single statement means. Okay, so I kind of see what you come up with. Sometimes this is not easy, but the first thing is just to kind of see on the 6 statements. If you kind of write down what the 6 statements mean, then I can kind of see if you got that part of the understanding. Yeah, okay, oh, that's right. Now, this, if your derivatives are 0, that's going to mean that you have tangent lines that are going to be horizontal. If the second derivative doesn't exist, it could be a sharp point, or it could be a vertical tangent line. That's what you're going to have to figure out when you kind of do the graph. And you have to erase sometimes on your graph. You're kind of off to a decent start on that. 5 is kind of where you're concave up, you're decreasing, then you're increasing. Okay? Then you got to kind of figure out what's going on over here. So we're off to a pretty good start. Okay? And again, if a derivative is undefined, either the first or second, what are the things we learn? Sharp point is a possibility. The other thing is a vertical tangent. Okay? And you'll have to figure that out kind of when you start drawing. Okay, so far it looks like we at least know what everything means. Okay? Okay, if the derivative is 0, that means that you would have kind of a situation where the tangent line is horizontal. Let's remember, a derivative gives you a slope of the tangent line. Yeah, so your graph's not quite right. You're going to have to do some adjustments. Increase, decrease, up, down. That statement 5 means that the derivative doesn't exist. That will mean that it's either a sharp point or a vertical tangent. Statement 6, the first derivative is 0. That means tangent line is horizontal. Okay? Derivative 0, horizontal tangent line. If derivative is undefined, it's either a sharp point or a vertical tangent line. Now, that's the fun part, is trying to put it all together. Right. Okay, decreasing, because it's saying the first derivative is less than. That means the first derivative is negative, so you're decreasing. The second derivative always tells you about concavity. Concave up, concave down. Okay? Well, that's concavity, that's a second derivative. Okay, so if the second derivative is positive, you're happy, so it's concave up, then concave down. If a derivative is undefined, it's either going to be a sharp point, right, or a vertical tangent line. If the derivative is 0, then that's a horizontal tangent line. So you have to make a note to yourself on that. Then you got to start seeing, you can start getting a graph. And getting the graph sometimes is the hard part. So let me see if anybody gets this. Nope. Yes. Okay. You're a winner. Okay. So you got it. That's what he's got. So you kind of what he came up with there. So when I check the students' work on this, okay, you are decreasing. You do have a derivative equal to 0. You are increasing, and you're concave up. All right, but here's kind of the problem is over here. Okay, you're concave up there. That's concave up. If you're concave down the whole way, then it's going to have to kind of go like this, and it's also increasing from 0 to 5. So you got to go like that, then you got to decrease, right? Okay, and the other thing is, you got to make sure when x is 0 that you don't have a derivative, that you have like either a sharp point or a vertical tangent. Okay, now you're doing a good job with writing notes to yourself. So one thing you can think about, let's look at it like this: concave up and concave down. Okay. Now, you got to kind of put everything together. So you might have something that's kind of like concave up, concave down. Well, what happens when x is -5, it's going to hit a low point. The derivative is going to hit be 0. So think about it going like that, hitting that low point. And that's -5, right?
And then 0.
Yeah, now the derivative is 0. So you would decrease as the graph, as you do that. So you're decreasing from negative infinity to negative 1. Then the derivative becomes 0. And then it changes to increase.
Oh, so it's just like 0, like
Yes.
the tangent line.
Yes, exactly. So it's like concave up. But at negative 5, that's going to be a minimum because you have the derivative equals 0. Okay? Now play with it from there and kind of see what you come up with. Okay, let's say concave. Let's start like this way. Negative infinity to 0. We're concave up. One way would be like this. Right? Okay. Happy face. Okay. Then you're going to change the concave down from 0 to infinity, so you could go like that. Now you have to kind of put all that together now. So if you're concave up and then concave down, well, put in your increase decrease step. Okay, you're decreasing from negative infinity to negative 5. So you're going to decrease. Then you're going to start increasing. Okay, so think about that. Decrease, increase, and that whole thing's concave up. Then down here, you're going to be concave down, but you're going to increase from 0 to 5. Right? You're going to decrease the rest of the way. Okay? So see if you can put it together. So, you kind of notice on that the hardest part is putting the graph together. So let me show you a couple of things that can help you do a little bit better job on that. Okay, let me go ahead and put this up here, and then we'll do the business example here. Okay, so let me show you a couple things on this. Everybody knew this pretty much automatically. Okay, you know that you're going to increase, then you're going to decrease, then you're concave up, you're concave down. The derivative's undefined. That's either a sharp point or it's a vertical tangent. And then this one is kind of step 6 is going to be you have horizontal tangent lines like that. Okay, 5 is kind of where everything is, things kind of change. Okay, this is what I recommend you do. And some of you did this and tried this. Basically, I'm going to just kind of write a note to myself that I am concave up here. Then I am concave down the rest of the way. Okay, but then it also, we need to look at increase, decrease. Now I'm just going to kind of put a couple of little dashed lines in here to kind of help me visualize what's going on. So if you look at this, this says we decrease, increase, decrease, then increase like that. So if you just write those notes to yourself, if you just at a minimum do that, because when I watch students do this, they always try to do it all in their head. Okay, let's just make sure we decrease. Okay, kind of look what I'm doing here. I'm decreasing, then I got to change directions and increase. Now, aren't I concave up by doing that? Yeah, that's concave up. And when you hit that low point, you're going to have a derivative that's 0. So you have to go like this, hit that low point, then start increasing. Now what's going to happen from there? Now it's going to start, hold on, did I get that right? I think this is, no, this should be increase, increase, then decrease. So I put that in on there wrong. Okay, so it's going to go like this. Let me adjust that here. Okay, so that's kind of how that goes. So now this is just kind of think about what's going to go on the problem. You're going to decrease, going to hit a low point, then you're going to increase. Okay, and we're concave up. Just by doing that right there, I've got everything accounted for in that problem, right? Now what's going to happen is I got to increase, I got to hit a high point, then I got to decrease. Well, I'm concave down. I do have the situation where I have that. But the other thing is this thing right here has to be a vertical tangent line. So you have to kind of draw that so it's like a vertical tangent line. Okay, so to me, that would be the best way that I could think of to kind of put that together. Just make notes to yourself. Up, down, decrease, increase, increase, decrease, and then that helps you put it together. You see what I mean? Write those notes to yourself. Okay? It's kind of challenging for students sometimes when there's that many conditions in the problem.
Where is the best place to start?
By doing these little notes to myself. Okay?
But like with which one do you think
Okay,
is
to
the best way
me,
to start?
the best thing is probably the decrease, increase, increase, decrease. Because then you automatically, you're just kind of thinking, okay, down, up. It'd be kind of like decrease, increase, still increase, decrease. And that right there tells you the shape right there. You just have to make sure that you fill in that whole thing's concavity, and that's where the derivative zero. Then you have to reason out that's the inflection point, and that's got to be a vertical tangent. So that's what I do, is I just start with increase, decrease, and then just kind of see if the concavity fits in there. Okay, that's the idea. Okay, all right, let's go to just doing an example of point of diminishing return. So I'll just kind of do that. And in business, what we mean by diminishing returns is this graph right here has three regions in it. It has region 1, region 2, and region 3 in it. So what happens on this is a point of diminishing returns. We're just going to kind of look at what happens on this region 1 and answer some questions on this. Okay, so if you're in region 1, and region 1, I'm going to highlight this in yellow right there. Okay, so what's happening is the rate of return is increasing. You can tell that on this region 1, that graph is increasing. Okay, the slope of the tangent line, and I probably have to stand up and kind of show this, or otherwise you might not see this well, is now I'm talking about the slope of the tangent line. Right now the tangent line's 0, right? But it's positive, right? Is my tangent line getting more steep or less steep? More steep. So the slope of the tangent line is increasing, okay? You ought to understand what I'm talking about by that. So your tangent line is increasing, okay? What are we? Are we concave up or concave down right there? Concave up. That's what concave up means, really, is the slope of the tangent line gets bigger. That's what it means, okay? So what we would get, since we're increasing, what's the first derivative if you increase? Positive or negative? Positive. What's the second derivative if you're concave up? Positive, okay? So that's what you get in that region 1, okay? So you're basically concave up and increasing is what that is. That's the key thing. Okay, so now what happens if we look at region 2? So in region 2, what you're going to find is you are still increasing. That graph is definitely still increasing. But what's happening, whoops, I think I did the wrong thing on that. I highlighted the wrong thing. So the rate of return is still increasing. But now look at what happens to the tangent line. This is what I want you to kind of wrap your head around. Okay, right here, look at my slope of the tangent line. See how that tangent line is getting less steep? Okay, this is what a point of diminishing returns is. The tangent line gets bigger, but then all of a sudden the tangent line starts getting smaller. That point of diminishing returns is going to change the concavity from up to down. So what it means in a business context is your rate of return starts slowing down. If that represented a graph of profit, it just means the profit's getting bigger, but it starts getting bigger at a slower rate. Does that make any sense? Okay, that's what a point of diminishing returns in. We call it diminishing because once you get past that point, your rate slows down. You're not growing profit at a fast rate like you were before. Okay, so what you would have in region 2, the rate is still increasing, but what the tangent line is doing is the tangent line is decreasing. You are concave down, and then that would mean since you're increasing, the first derivative is positive. Since you're concave down, the second derivative is negative. So what a point of diminishing returns is, in very simple calculus terms, all in the world it is it's a point of inflection. Okay, that's what it is, and that's why point of diminishing returns fits in well with concavity. Okay, and this is pretty typical business concept. Have you all ever learned about that concept in a business class before? No? You have? Okay. All right. So that's why, and you can explain that to a non-calculus student, but calculus, I think, clarifies it a little bit further. Okay, so we're going to go on down and do this example 7, and we'll kind of do this real quick. Just finish this one up here. So when we find the point of diminishing returns, all we have to do is do the second derivative and set it to 0. Okay, so the first derivative is going to be 9x squared minus, and then by power rule, that would be x to the third. Your second derivative is going to be 18x minus 3x to the second. Okay, you're going to set that equal to 0 to get critical values. So we need to factor out a 3x, and I'm going to have to do this kind of fast, but we have worked on this quite a bit today. So that's going to be 6 minus x. So your critical numbers are going to be x equals 0, and the other critical number will be x equals 6. Okay, so when you do a diminishing returns, it's just all about the second derivative. That's what you need to do. Okay, now what we're going to do is we're going to do a sign chart. And in this problem, I gave you that we're only interested in the interval from 0 to 9. So we have the derivative is 0 at 0, and also the derivative is at 6 was also 0, like that. So what you would have to do on this then is, and this is an easy enough problem to just use test points, so I'm going to use a point between 0 and 6. I'm going to plug it into the second derivative. So that's 18 times 1 minus 3 times 1 to the second. And that's positive. That means the graph is concave up. I'll do a test point between 6 and 9. I'll plug in a 7. So if I do that, again, we plug that in. We'll do 18 times 7 minus 3 times 7 to the second. You will get a negative. You can do that on your calculator, so that means you're concave down. So when you do a point of diminishing returns, this is what you expect to happen. You're going to be concave up, then you're going to be concave down, and you're going to have that inflection point right there. So that is the point of diminishing returns. So what we would say in this problem is the point of diminishing returns would happen at 6, comma, whatever that y value is. And we could get that y value by graphing on a calculator. All right, so again, what this is saying is, and let me stand up and just pass on, show my tangent line right here, is right here, the slope of the tangent line is getting bigger. So that means the rate is increasing from 0 to 6. Then the rate is decreasing when the tangent line gets less steep. So the rate of increase is not the same as just increasing. If I say rate of increase, then you're talking about derivative number 2. Okay, so what we would say is that would be 0 to 6. The rate of decrease would be from 6 to 9, like that. Okay, and basically what you could do on this real quick, and I'm just going to do this on the calculator, real quick on this. You don't need to do this because I'm about out of time here. So if I graph 3x to the third, and then minus 0.25 x to the fourth, and then what else got? Plus 200. Okay, and I'm going to do a window of 0 to 9 because I was given in the problem. I'm going to do 0 to 800. You don't have to do this on the calculator. I just want to show you what happens in the problem. Okay, so here's my graph. Okay, and if we trace at 6, that gives you your inflection point. So that point right there would be 6, 524 would be your point of diminishing return. So in the context of this problem, what they were saying on this is kind of like your advertising. Like that, you put $1,000, $2,000. When you put $6,000 into advertising, this is the number of televisions that you sell according to the problem. So that's just where the tangent line gets bigger, the rate of increase is getting bigger, then it slows down. Does that make sense? So if rate of increase gets bigger, then starts slowing down. That means you're going from concave up to concave down. Okay? Well, that's what diminishing returns is. In a calculus class, all you got to do is kind of work with the second derivative and make the sign chart. That's how you figure it out. Okay? All right. That'll take care of us for today then. So hopefully next Monday I'll have like everybody on time. Can you give me a promise? Please, please, please. Okay? You're going to miss out. What's that? Test 3 is 2 weeks from today. 2 weeks from today. Still got 2 more kind of sets of notes that we go through.